Hello everyone, it's March the 7th. I'm tired. A full day of coding. I learned something, learn about a new package, a new library in React Native called React Native Snap Carousel. Very, very well written. Actually, I don't know if it's well written, but the user experience is very nice, very, very nice. And I was, we were trying to write this type of carousel scrolling. We're trying to write this animation on our own, manually. But this manually doing this is it's pretty hard. So eventually we gave up. And then there's a open source um, thing that people have written already. Why not just use it, right? So save time for us for sure. All right, let's see what we have today. Linked list cycle. All right, this is an old problem. 141. Oh, it's a year ago we solved this. If has a cycle in it. Yeah, we can just go right ahead. This one has been criticized in the past, I remember, but I don't really think it's the criticism is valid. I think this is a good problem. It helps you understand linked list more, and especially the follow-up question, right? The follow-up question is identify from where the linked list starts, from where the circle starts. And to do that is just, when you meet at this position, you put a slope back, and then they go the same rate, and the next time they meet each other, that is the starting point. And there can be a mathematical proof for that. But anyway, that's not our purpose. So we just go slow and fast. While fast and fast dot next. Fast equals fast dot next dot next. Slow equals slow dot next. All right. If has a circle in it. All right. So while fast, right? And then if slow is equal to fast, return true. Otherwise, return false. I think this shall be sufficient. Actually, let's check it first. All right. Wait, hold on. Is this one considered? There's no cycle. So we have to check it later. Not check it first. Yep. You want to try empty? Yeah, we should try an empty node. Who knows, right? Oh, there's a position. What is this position? Oh, position's not passed. This is empty. Empty array. Yep. I think we're good. Yep. We're good. 613. One 41. very classical and old problem. 2 pointers, one slow and one fast. If the slow catches up fast, there must be a cycle. When 60, 79. Alright, nothing much to say about this. I just call it. Alright, that's the real one. Logical OR of 2 binary grids represented as quad trees. The heck is this? Oh, quad trees. That means each node has 4 children. A binary matrix is a matrix in which all the elements are 0 and 1. Given quad tree 1 and a quad tree 2, quad tree 1 represents an n by n, another n by n. Return a quad representation of n by matrix, which is the result of logical bitwise OR of the 2 binary matrices represented by, okay? You can assign the value of a node to true or false when leaf is false, and both are accepted. A quadratic is a strategy where each internal node has exactly 4 children. Besides, each node has 2 attributes. Bow is leaf. Oh wow. Top left, top right, bottom left, bottom right. From a 2-dimensional area using the following. If the current grid has the same value all ones, all zeros, set is leaf to true, and set val to the value of the grid, and set the 4 children to null. So it will stop if the 4 of the current grid is the same value. I believe here the grid referred to is an n by n, right? That's the grid. If the current grid has different values, then it leaves to false and set val to any value and divide the current grid into, so val to any value divided into 4 subgrids, because for each of the children with a proper subgrid, okay? The input represents a serialized format of quad tree using level order traversal, while no signifies a path terminator when no node exists below. If the value of this or this is true, is 1 in the list. It doesn't matter because what I get is a quad tree, so it's a different thing. Is a leaf? No, because there's different values, so we go 4. And top left is leaf. Top right is leaf. Both are leaves. All of them are leaves. Quad tree 2. Top left is 1, 2. apply bitwise OR. Binary matrix is shown not only for illustration. You don't have to construct the matrix to get the results. I suppose some people might want to create a binary tree, but not binary tree, but create the matrix. But for us, it's a tree, right? So let's just do this directly. Okay, directly. How? Well, the division of, and I'm pretty sure n equals 2 to the x. Yeah, I'm pretty sure that it definitely have to be. Wait, hold a second. What if x equals a 0? What if it's a 1 by 1? If it's a 1 by 1, what do I do? Oh, that it's a leaf by itself. Yeah, it is a 1. It's a leaf by itself. And also equal to 2. A 2 by 2, which is fine. And then 4 by 4. And then 8 by 8. Okay? Yeah. So we have two trees. The first tree, then we can go to the first level, right? They always have first level, unless it itself. Hold on. And say both are of the same size, right? Yeah, both of the same size. So what do we check? We check if the we check if the current is a leaf. Well, if both are leaf, that means they're the same. Then we can do this exclusive. We can do the OR, right? If one is leaf and the other is not leaf, we can check if the one is leaf, if value is 1. Oh yeah, if the value is 1, then it doesn't matter on the. Hold on. The only thing we cannot do is if both are not leaf. If both are not leaf, then we have to keep going. But as long as one of them is leaf, then we immediately know the result. Because the prerequisite for being leaf is if you're all ones or if you are all zeros. There are two situations. If you're all ones, then OR will be all one. If it's all zero, then OR will be the other party, right? So, okay, that is a saving, right? That is good. But how do I construct? Oh, we can return. We can return the node, right? We can return the node. Yeah, so from the start, and I have 4 nodes, and then, we just, each node, we do the comparison, right? Each node. So we're given a current node, right? Current node, if the current node, one of them is, then we're just going to return a node that was the same value as this. And let's try. I mean, the idea is not fully developed, but I do think it helps me more if I simply just, write it. The process of writing the answer helps me think, especially right now, because right now I feel a little bit mushy. I started to feel mushy, which is not a good sign, and I don't want to feel mushy. Alright, so that's the node, and of course I'm not going to use this notation. This is like type hint back in the old days. Alright, so quadtree 1 and quadtree 2. So we just say if, right, quadtree 1 dot is leaf. Well, quadtree 1 is leaf, then we immediately know the result, right? Then we're going to return a node, right? Yeah, I like to do this. Okay, so if quadtree 1 is leaf, then it depends, the value depends. If quadtree 1 dot val is equal to 1, then we're going to return a node with val equal to 1 is leaf equal to true. That's it. Else. So that's a 0, right? Then we're going to return node. Ooh. Does that have to be a completely new node? Do I have to copy every single thing? That's fine. It's just yeah, it's fine. It's just different. Like the same node can have different parents pointing to it. I think it's fine. Might as well I just return. Yeah, in this case, I just return quadtree 2. Now why don't you return just quadtree 1? All right. Or we just return quadtree 1. And then if quadtree 2 dot is leaf, return quadtree 2 if quadtree 2 dot val is 1, else quadtree 1. Yeah, I can do this. Let's say return this if, then else this. So these are the edge cases, right? Now, neither is leaf. And then we just go for the child, right? Go for child. Then we simply create a new node, right? We say node equals node, val equals, that's -1, doesn't matter. Is leaf is equal to false, okay? And then node dot top left shall equal to self dot intersect quadtree 1 dot top left, quadtree 2 dot top left. And then we just copy this for, oh, holy shoot, this is the top left, right? And then here, we just do, now in the top left, top right, this is what? This is this, bottom right, bottom left. Yeah, maybe you want to do bottom left first, and then return node. Okay. I'll use my quad tree definition for this. Not sure. I'm just guessing. I think this is what it means. Yeah, looks to be good. You should test the empty case, man. Oh, wait. What the hell is this? Wait, hold on. Top 1 0 0. So top left is 0. Top left, top right, bottom left, bottom right. Okay, that's 1. Second one, top left, top right, bottom left, bottom right. No, top left, top right, bottom left. Wait, hold on. Is leaf and vowel. Okay, is leaf and vowel. So is leaf and 0 0 1 1 is leaf and vowel 0 1 1 0 1. Okay. So it should be 1 1 1 1. What did I get? Shoot. Okay. That's So if all 4 children the value is the same, yeah, that should be another check. So if shouldn't do this. I should just say top left, top right, bottom this, right? And if top left dot vowel, top left dot is leaf. Oh my god. So they all have to be leaf, right? And then the value has to all be the same. And all right, TL, TR, BL. All right, if TL dot is leaf and TR dot is leaf and BL dot is leaf and BR dot is leaf, all right, and TL dot vowel equal to TR dot vowel equal to BL dot vowel equal to BR dot vowel. If this, then we shall return a new node with vowel equal to TR dot vowel is leaf equal to true. Else, when I return node vowel equals, doesn't matter, is leaf equal to false, and top left equals TL, top right equals TR, bottom left equals BL, and bottom right equals BR. That will be my solution now. Make slight change. Okay. Alright, let's use this as our test case. Can do this, right? Empty case. Oh, we need a 2. Shoot. Because it does say it can be 0. Oh, it has to be 1. X can be 0. So the length has to be 1. So this is not valid. Which is fine. Doesn't matter. Yep. Alright, let's try this one. I did an extra check. Yep, extra check, make it right. Alright, this problem might seem complicated, but once one understands how the data structure, how the quad tree works, it's quite straightforward using recursion. And one important observation is that if one of quad tree is leaf, we already have we already hit the anchor case. If neither of the quad trees are leaf, we need to evaluate each of the 4 subtrees and then combine the result. The combination is important to identify whether all children have the same value. What's the runtime on this? Worst case scenario, we go 4 levels, right? The top, we go 4 levels, go 4 levels. Yeah, I don't know. What's the runtime on this? Too lazy to think. What's the runtime on this? But they're O(n) squared, at most O(n) squared. The solution is pretty much the same. I'm simply just curious on the runtime. This one says log n. I'm not sure. worst case scenario, because every node gets visited once. So worst case scenario is O(n) squared, but best case scenario is O(1). I don't know. What is the average case? If you think about it's split into 4, right? Every level is split into 4, and the merge cost is 1, right? Merge cost is O(1). And then you have O(n) squared starting. Yeah, it does feel like the O log n. Yeah, because the levels you have, every time you split 4, you split 4, you split 4, so that's the log n. The depth is log n, and then the merging cost is O(1), that's why it's O log n. I actually agree with O log n. $83, $58. Okay, that will be it. It's not too hard. All right, I'll see you guys tomorrow. Adios.